Hello, this work is titled Markov Model for the Flow of Nanobots in the Human Circulatory System. The author comes from two different universities, University of Lübeck and Technical University of Berlin. We are Regine, Anke, Ketki, Lucas, Professor Dresla, and Jorge. The development of new mechanisms for targeted drug delivery is a focus of attention in medicine and pharmaceutics. Through nano-devices traveling in the blood vessels, the release of drugs is targeted to specific regions without affecting healthy tissues around. This mechanism aims to improve the poor pharmacokinetic properties of most therapeutic drugs. Equipped with communication and guiding system, nano-devices are guided by passive means driven by the direction of blood vessels or by active means driven by external sources to the human body. However, such applications are only reported for a specific path through the blood vessels, without analyzing the human circulatory system as a whole. In a different approach, we consider the continuous flow of nanobots through the human vessels along its closed loops. We statistically analyze the location of nanobots driven by the blood flow through arteries, capillaries, and veins. The problem becomes challenging because of the several bifurcations in the blood vessels. For instance, a particle traveling through the arcus aorta will randomly jump to the head or to the lower body, and its closest path through the blood vessels will be randomly selected, depending on the performing jump on the bifurcation. Considering this random selection of the traveling path, our intention is to derive the stationary distribution of nanobots in the different vessel segments. This is useful, for instance, to analyze disease detection capabilities through the vessels. As exhibit this figure, nanobots traveling close to the disease may detect and provide an alert of this issue. However, depending on the amount of nanobots, the detection capabilities will be better performed. In this work, we provide a methodology to compute the total of nanobots per vessel segment. On our methodology, we rely on the equivalent representation of the human circulatory system by a Markov model. Considering that the human vessels form closed loops, then the traveling path of nanobots through the vessels can be modeled by a sequence of steps as staged in a Markov model. However, to have a complete description of the Markov model, we need to find the transition matrix pi. To that end, we relied on the electric circuit representation of the human vessels to properly derive the corresponding transition probabilities of the Markov model. Summarizing, the methodology consists of the modeling of the traveling path of nanobots through a Markov model and to compute the transition probabilities based on the electric circuit representation of vessels. The Markov model is represented with a total of 24 stages corresponding to the arteries, the capillaries, and the veins of the human circulatory system. The stages are connected as the vessels represented here in this figure for the human vessels. To find the transition probabilities, we represent the Markov model by their closed circuits. Here represented are 5 loops following the diagram of the human system here on this figure on the left. Based on this representation, then the transition probabilities can be directly computed as the ratio of flow from the human circulatory system. For instance, the transition from S3 on the left heart to S10 on the thoracic aorta can be computed as the ratio of the flow through the thoracic aorta by the flow through the arcus aorta. In this regard, the transition probabilities here defined on each bifurcation will be dependent on the flow through the vessels on each respective bifurcation. Then, to compute the different flow values per vessel segment, we implement the electric circuit representation of the human circulatory system. A connection of analog elements like resistors, inductors, capacitors, diodes, and source voltage are used to derive values for pressure and flow in the blood vessels. For instance, the pressure will be analogous to voltage, while the flow will be analogous to the electric current. Based on this model, we can then compute the flow on each bifurcation and the corresponding transition probabilities. The circuit is implemented in Simulink MATLAB by properly connecting the above electric blocks as represented in this figure. To validate, this electric circuit model provides a curve of pressure according to the physiological parameters of a standard person. Larger amplitudes are provided in the arteries, while the lower amplitudes will be given in the vessels. Following this model, the resulting transition probabilities are obtained as depicted in this diagram. Following the blood flow, all the direct path will have a transition probability equal to 1. On the bifurcations, this was computed based on the resulting flow per vessel segment. Here we can see, for instance, that for a given nanobot at stage S3 on the left heart, it is more probable to jump to the lower body than to the upper body. This is in correspondence with the total of circuits to be connected on the lower body in comparison to the only one in the upper body. We also derive the probability for a nanobot to travel through these different 5 loops. As expected, there is a similar probability to travel through these loops. There is not any preference. This is except for the lower mesenteric, where the resistor value in the electric circuit representation is the highest, and the flow corresponding to this path is the lowest, and correspondingly it is less the transition probabilities in this case. Furthermore, to validate the Markov model representation, we also model the flow through the blood vessels on the BloodVoyagerS framework. BloodVoyagerS derives the location per nanobot in the human circulatory system according to the achievable speed per vessel segment. In the arteries, 10 cm per second, 1 cm per second in the capillaries, and 3.7 cm per second in the veins. In this graph, we provide the main results of this work. These bars represent the probability to find a nanobot per vessel segment. Comparatively, both solutions on the BloodVoyagerS and through the Markov model obtain a similar distribution of nanobots in the human circulatory system. The largest concentration of nanobots will be on the lungs and on the heart, followed by the thoracic aorta and the vena cava. The lowest concentration will be on the arteries and veins in the legs. As concluding remarks, we would like to highlight 3 main concepts. A low complex model is derived to locate the flowing nanobots through the human vessels. That is, the model is comprised by a Markov model representation of the human circulatory system, where the transition matrix can be directly computed based on the blood flow, which can be given by the corresponding electric circuit model. Secondly, the model can be extended to consider time variable transition probabilities, that is, to analyze the impact of variable blood flow in the distribution of nanobots. For instance, we can consider daily activities like exercising, walking, resting, eating on the distribution of nanobots per segment. Considering that the transition probabilities are dependent on the blood flow, the electric circuit representation may provide this time dependency by properly tuning the values of resistors, inductors, and capacitors. Finally, this model might be also extended to analyze the delays in application where we want to monitor disease or to deliver drugs into specific body regions. For instance, if we have external gateways connected to the human body, like this one connected in the heart, then it will be rather useful to derive the delivering delay of sensory results at the gateway. Depicted here is the case where bacteria are causing an infection, and this infection, after detected by the flowing nanobots, wants to be alerted through a monitoring center through the gateway. By means of the Markov model, we would like also to extend this work to characterize the randomness of information delay because of the random path taken by the nanobots. We thank for your attention, and we are open to receive questions and to collaborate by the contact mail here on this slide. Thank you.